I think you've noticed how, in the past few years, we've developed a trend for loud headlines claiming that the James Webb Telescope has supposedly shocked scientists, broken science, and so on. And while there's obviously some exaggeration there, these stories don't come out of nowhere. Webb's new data really does surprise us quite often. If the story with giant galaxies in the early universe is still ongoing, and we've talked about it more than once, something new has appeared in parallel. One scientist analyzed a set of galaxies in Webb's data and found hints that our universe might actually be enclosed inside a black hole. How about that? So, in this episode, we'll dive into a seemingly wild, yet entirely scientific idea: black hole cosmology. Like many bold ideas in cosmology, this one didn't appear yesterday. It dates back to the mid-20th century. That was the time when scientists had just realized that black holes weren't science fiction but real objects that could form from the collapse of stellar cores. Almost immediately, theorists began asking, what if the universe itself is trapped inside one of them? Sure, it sounds fantastical, but only until you notice a few striking similarities between the universe and black holes that are hard to ignore. For example, black holes are thought to contain a singularity, a point of infinite spacetime curvature, infinite energy density, and a place where time stops. The same thing was expected at the beginning of the universe. If you extrapolate time backwards to the moment of the Big Bang, you arrive at a kind of singularity as well. Besides that, black holes famously have an event horizon, a boundary beyond which even photons can't escape due to the extreme curvature of spacetime. Our universe also has its own kind of event horizon, a cosmological one, the limit past which light from external objects simply can't reach us. For details, you can check out this video. So if singularities and horizons seem like interesting coincidences, here's another one. It turns out that the Hubble radius of our universe is equal to its Schwarzschild radius. In simple terms, the mass of all matter in the universe corresponds to the mass of a black hole with a radius of 13.8 billion light-years, which, by the way, is the radius of the observable universe. Of course, due to cosmic expansion, its actual size is much larger, but 13.8 billion light-years is our cosmological horizon. So again, if you take the total mass energy of the observable universe, you get a black hole the same size as the observable universe. Here's another fun conclusion. The radius of a black hole is directly proportional to its mass, while its volume grows as the cube of that radius. This means that the bigger the black hole, the lower its density. And a black hole with a radius equal to our universe would have roughly the same density as our universe. Another coincidence? Sure, maybe. But let's be honest. It's more than enough motivation for scientists to at least consider this as a potential clue to the true nature of the universe. Well, besides the interesting similarities, there are obviously some major differences too. First of all, by definition, a black hole is a region of space from which nothing can escape. And if it's a region of space, then logically there should be some other region of space outside it, something beyond its boundary. But as you probably know, we don't usually talk like that when it comes to the universe. In cosmology, the universe is everything. The totality of all matter, all energy, and crucially, space and time themselves. There simply can't be anything outside the universe if the universe, by definition, is all there is and everywhere there is. You might say that's a weak argument because the important part isn't what lies outside the universe black hole, but the fact that the universe looks like a black hole from the inside. But that's not quite right either. You've probably noticed that the universe is expanding, not contracting. Inside a black hole, you'd expect matter to collapse into a single point, but in our universe, everything is moving away from everything else. So, according to general relativity, our universe had a singularity in the past, from which everything emerged, not a singularity in the future, which is what you'd expect for matter falling into a black hole. So if we're talking similarities, the universe actually looks more like a time-reversed black hole, or, as it's usually called, a white hole. And here's where things get complicated, because that concept is a lot more speculative. Unlike black holes, white holes haven't just failed to be observed. There are serious doubts they can even physically exist. Still, let's not rush to conclusions. Instead, let's take a closer look at how cosmologists who study black hole universes actually imagine its physical nature. Because as you'll see, The fact that it expands instead of collapses doesn't scare them at all. The first and most solid version of this idea comes from the Polish physicist Nikodem J. Popławski. Back in 2010, he showed that if you modify general relativity, black holes actually start to look much more like our universe. His idea is based on a theory of gravity called the Einstein-Cartan theory. Yes, it's one of the modifications of general relativity, and most importantly, it allows us to completely get rid of those unpleasant things called singularities. As you know, a point of infinite energy density is just a mathematical artifact, a sign that we don't understand the physics under the conditions we think exist inside black holes. In classical general relativity, when matter collapses under its own gravity, its density and the curvature of spacetime grow essentially without limit. But the Einstein-Cartan theory adds something new. It considers not only the mass of particles, but also their spin, their angular momentum. The idea is that along with mass, particle spin can also influence spacetime through a phenomenon known as torsion. To simplify it, if mass bends spacetime the way a two-dimensional sheet would sag under weight, spin doesn't just bend it, it twists it a little. This effect is completely unnoticeable almost everywhere in the universe, except in the most extreme environments. So inside a black hole, where matter is compressed to unimaginable densities, not only energy density but also spin density comes into play. And what does that mean for the collapse? When the density of matter approaches Planck scale values, the contribution from spin creates a repulsive interaction between fermions. Elementary particles literally start repelling each other. This repulsion grows faster than gravitational attraction. So instead of further collapse, you get an effective counterforce and a force strong enough to actually win. So the collapse of matter literally stops, and a reverse process begins. Simply put, a bounce. At this point, inside the black hole, instead of contracting, everything begins to move away from everything else. As you've probably figured out, Popławski sees this very bounce expansion as the explanation for what we call the Big Bang. In his view, the universe is nothing more than a black hole, a pretty large black hole to be fair, that didn't collapse into a singularity, but instead continued its evolution through expansion. Now you might object, have we ever seen black holes in our universe that expand exponentially? Why doesn't Sagittarius A star, for example, behave like that? Popławski's model explains that this shouldn't happen, at least not from our perspective as external observers. Imagine a massive star collapsing gravitationally and forming a black hole with an event horizon. According to the Einstein-Cartan theory, the matter inside doesn't fall into a singularity, but instead bounces and expands. Now, for an observer inside the event horizon, what happens looks exactly like what we see in our universe: expansion. But for an observer outside the horizon, nothing happens at all. That's the key feature of this cosmological model. The expansion of matter inside a black hole does not show up on the outside. Why? As you probably know, objects falling into a black hole never actually cross the event horizon from the perspective of a distant observer. They appear to freeze on it. It's one of those weird effects that completely breaks your intuition when you think about it. But this freezing happens because of gravitational redshift and time dilation, effects that only grow stronger as an object approaches the black hole. But this slowing down is only seen by the distant observer watching from afar. They notice that the falling object's clock runs slower and slower until it appears to stop entirely at the event horizon. For the falling observer, however, things look completely different. Nothing special happens at the horizon. They just continue falling and enter the black hole. Inside, they can observe compression, bounce, expansion, whatever transformations the universe goes through in their local frame of reference. But not the external observer. They live in a different reference frame, in a different flow of time, if you will. And for them, the falling object never actually falls. By the way, these frozen silhouettes don't remain on the event horizon forever. You won't see everything that ever fell onto a black hole sitting on its surface. Due to gravitational redshift, the image becomes redder and dimmer until it disappears from view completely. The main point is, formally, for the distant observer, the moment of crossing the event horizon never actually happens, or happens only after an infinite amount of time passes in their reference frame. The same goes for everything that happens inside the black hole. It all takes an infinite amount of external time, which means that for those far from the black hole, the bounce never occurred and never will. For them, the black hole is just a black hole, nothing more. In this way, black hole cosmology becomes a kind of multiverse model, where every black hole in the universe is essentially its own separate universe. A black hole gives birth to a new universe inside another, acting as an Einstein-Rosen bridge, a gateway connecting the new universe to its parent. Each black hole, each new universe, is its own branch of spacetime with its own timeline. For those inside, it can exist infinitely long and expand indefinitely, while for those in the parent universe, it's simply an ordinary black hole. Of course, you can't just create a cosmological model and declare it correct, even if it sounds incredibly impressive. Every new model has to solve the problems of the previous one. Otherwise, what's the point of making it? And black hole cosmology actually succeeds at this. It explains the weak points of the Big Bang model, in particular that mysterious singularity, and even cosmic inflation. Inflation is the period in the first moments of the universe when, hypothetically, an extremely rapid exponential expansion took place. To explain that expansion, theorists had to introduce hypothetical fields with odd properties and other speculative ideas. But the bounce naturally produces the required expansion and explains why the universe is so homogeneous and isotropic. On the other hand, as often happens with beautiful theories, there's nothing that can actually prove it true. No astronomical observations pointing to it. One potential way to test it might lie in the geometry of spacetime itself. Since black holes are spherical, the universe might be spherical as well, meaning spacetime could have some curvature that we might be able to measure. So far, the most precise measurements based on the Planck satellite's observations of the cosmic microwave background show that the universe is flat, at least within the margin of error. But nothing stops us from building more advanced instruments that could reveal tiny deviations from flatness, deviations that would indicate a globally curved universe. In any case, strange as it sounds, we still don't have any conclusive evidence against this cosmological idea, but also no convincing evidence for it. However, the need to modify general relativity is its obvious weakness. There is no experimental confirmation that the Einstein-Cartan theory works, or that the spin of fermions really affects spacetime. And since good old GR hasn't failed us yet, any deviation from it can be considered somewhat speculative. But in May 2025, we saw a new, in my opinion, even more interesting version of black hole cosmology, this time from researchers at the University of Portsmouth. Their team proposes a new approach to removing singularities, relying on quantum mechanical effects rather than modifying general relativity. Overall, the idea is similar to Popławski's model, but the authors base it on the well-known degeneracy pressure that halts gravitational collapse. One of the fundamental properties of matter at the level of elementary particles is described by the famous exclusion principle proposed by Wolfgang Pauli. This principle tells us that no two quantum particles that belong to fermions, such as protons, neutrons, and electrons, which make up ordinary matter, can occupy the same quantum state. For electrons, for example, this means that only two of them can be on the same orbital in an atom at the same time, and only if their spins are opposite. For our story, we can simplify it. Quantum mechanics forbids electrons from piling up on top of each other or squeezing into the exact same spot. This, by the way, explains why matter occupies space exclusively for itself and doesn't let other objects pass through it. Literally all matter in the universe is stable thanks to this principle. But the universe is a strange place, and there are situations where gravity tries to break this rule. It compresses matter so strongly that particles simply have no choice but to approach each other to a critical distance. The elementary particles respond with an outward force, the so-called degeneracy pressure. So if this property of matter explains objects like white dwarfs and neutron stars, then why couldn't it also prevent black holes from collapsing into a singularity? That's exactly the question Enrique Gastonaga and his colleagues asked in their new study. At first glance, this seems illogical. Aren't black holes the ultimate proof that degeneracy pressure does lose to gravity sooner or later? Yes, we have white dwarfs supported by electron degeneracy, neutron stars supported by neutron degeneracy, and even hypothetically quark stars supported by quark degeneracy. but all of them inevitably collapse into black holes once they exceed a certain mass threshold. But the authors of this paper argue that the Pauli exclusion principle must still apply even beyond the event horizon. They insist that under no circumstances can two fermionic entities occupy the same state, even inside a black hole. They literally suggest that some other yet unknown form of degeneracy pressure might exist, assuming electrons and quarks are not truly fundamental particles. So a true singularity is prevented by some absolute density limit that exists under conditions we cannot observe. And from there, everything proceeds just like in Popławski's model. Mathematically, repulsion at the threshold of absolute density produces a bounce, followed by the expansion of the universe. And all this happens within standard general relativity, no modifications needed. Moreover, the authors write that their model is fully consistent with inflationary expansion and even with the accelerated expansion of the universe, which we usually attribute to dark energy, meaning there's no need to invoke exotic physics anymore. They even propose a logical explanation for dark matter, suggesting that during the collapse of matter into a black hole, regions of higher density might have formed, which later became primordial neutron stars and black holes. Here's the quote: "If such objects are sufficiently abundant and long-lived, they could naturally provide a candidate for non-particle dark matter within the BHU, black hole universe scenario." The authors believe that these early relics of the universe could serve as strong evidence supporting their model. However, the weak point here, of course, is the requirement that the exclusion principle must hold inside a black hole. This implies the need for some hypothetical form of degeneracy pressure and even hypothetical particles more fundamental than quarks and electrons. But the main problem remains unchanged: experiment and observation. Without them, any theory is nothing more than a set of equations. How can you prove something that, by definition, cannot be checked observationally because all the physics is hidden behind an event horizon? However, if our universe is inside a black hole, then there is no need to peek inside other universes, right? It's enough to look at what's happening around us. One possibility, especially important for the model we've just discussed, is that the universe has a slight positive curvature, and we've already mentioned that a more precise instrument could, in principle, detect it. In addition, there is another property of black holes that might be observable: their rotation. Since these objects naturally rotate, the corresponding universe inside them should inherit this rotation as well. So, can we test this? Well, at least one researcher claims he already has. Lior Shamir from Texas Tech University decided to examine the rotation direction of spiral galaxies. For this, he used James Webb data from its early science program, the Advanced Deep Extragalactic Survey. To determine which way a galaxy is rotating, you don't need complicated spectroscopic observations. You can even do it yourself simply by looking at the spiral arms. The direction in which they twist tells you the answer. Shamir's work is based exactly on this type of analysis, but performed not manually, via a computer algorithm. The galaxies he selected were located near the galactic pole, meaning in a direction perpendicular to the plane of the Milky Way. Studying local galaxies like this makes it possible to unambiguously determine their rotation direction relative to us. The author then removed from the sample all galaxies whose rotation direction could not be reliably established, ending up with a set of 263 objects. The result turned out to be quite intriguing. 105 of these galaxies rotate counterclockwise, while 158 rotate clockwise. In other words, for some reason there are 50% more clockwise rotating galaxies. This is very strange, because a foundational principle of cosmology states that on the scale of galaxies and galaxy clusters, the universe should look the same in all directions. Put simply, Shamir should have seen an approximately 50-50 distribution, but instead, he found that 2/3 of the galaxies rotate in a particular direction. So what does this imply? The author believes that such an asymmetry cannot be random and may potentially be a signature of a rotating universe. And when considering possible explanations for this rotation, he leans toward the idea of a universe inside a black hole. It must be said that in his study, he acknowledges that there are other possible explanations for the observed asymmetry. For example, it may simply be an illusion for an Earth-based observer. The thing is, we ourselves move around the center of the Milky Way, so due to the Doppler effect, galaxies that rotate in the opposite direction to our motion will appear slightly brighter, while those rotating in the same direction will appear slightly dimmer. As a result, we would naturally notice more galaxies that rotate opposite to us. Shamir, however, argues that this is not the main cause, emphasizing that the effect on galaxy brightness should be minimal. Still, it's important to remember that he had to exclude many galaxies whose rotation direction couldn't be determined, which leaves room for bias. Moreover, this is not the first study to examine galaxy rotation direction, and previous ones covered many more galaxies than 263. In fact, thousands or even tens of thousands. None of those studies found any significant asymmetry. But even if we assume that the universe truly has some preferred axis of rotation, that doesn't automatically imply the black hole cosmology model. Yes, black holes do rotate, but we still need to understand how such rotation would influence the universe on cosmological scales, and even how it would affect the rotation of galaxies themselves. Whether this particular work qualifies as the first piece of evidence is for you to decide, but in my opinion, we need something much more substantial. Overall, regarding this whole topic, I must admit I was surprised by how many interesting nuances here actually echo features of the observable universe. Do we truly live inside a black hole? The short answer is, probably not. But this is one of those ideas you can't just dismiss for being exotic. As long as there is no convincing evidence against it, we shouldn't claim it's fundamentally impossible. I can only imagine how astronomers would react if they eventually had to accept that we exist inside the strangest objects in the cosmos. Psychologists would definitely get a lot more work. Not everyone could handle such a realization. Still, if you want to live in a black hole, or believe you already do, leave a comment under this video. And that's all. Thank you for watching to the end and leaving a like. See you in the next episode.